Hello and welcome to the course of the problems of thermal protection in buildings. Today we will try to solve the heat conduction equation within a wall where, as boundary conditions, we have an assigned temperature and a heat flux on the other surfaces. This case may be typical in buildings if from one side of the wall we furnish power. So it is useful to try to solve it by applying a heat conduction equation. We will start from the complete and general form of the equation, and then we will simplify according to our problem. We neglect the terms that are not involved in our problem, and we will get an analytical solution for our problem. So, let's consider a plate of thickness L with a determined length along the z-axis and along the y-axis. But we assume that the thickness along the x-axis is much smaller than the dimension along the y and z axis, and so this allows to simplify the problem. Let's see how. We know that we have an assigned temperature on this wall, let's call it T1, and we have an assigned heat flux, let's call it Q dot, on the other wall. So we have a conduction problem, because the wall is made up of a solid material of thermal conductivity K. The equation which characterizes this problem is the general heat conduction equation that we can write in a general form. So we have nabla scalar K gradient of temperature, which is the divergence of the temperature, plus volumetric heat generation is equal to rho density times specific heat times the derivative of temperature with respect to the time, let's call it theta. So this is our equation. But as you can notice, there are some terms that in our case may be neglected. For example, let's start to consider the derivative of temperature with respect to time. Our problem does not give us information about the time behavior. And we know that there is an assigned temperature on one wall and a heat flux on the other wall. If we consider this problem stationary, so we don't want to study the time behavior of our system, we can simplify the equation, because the derivative of temperature with respect to the time would be equal to 0. Therefore, we can cancel this derivative, and the equation simplifies in the following way. Nabla scalar thermal conductivity times gradient of temperature plus volumetric heat generation equal to 0. So our equation is now simpler because we have a term we neglected, we deleted one term of the equation, and we reduced the number of variables on which our problem depends on, because we deleted the dependence from time. So, this is a first step in our simplification process. Now, let's try to understand if we have volumetric heat generation in our domain. Volumetric heat generation is present, for example, when we have electric cables in a volume and these cables generate heat because of Joule effect. Or volumetric heat generation can be linked to chemical reaction. For example, isothermal chemical reaction release heat, and this heat can be seen as a volumetric heat generation. Or if we think to nuclear reaction, also in that case we have a release of heat. In fact, they can be treated as volumetric heat generation. But in our case, we have a wall, a planar wall, and no reactions, no electrical cables are considered. Therefore, we can assume that volumetric heat generation is zero in our volume. So we can neglect also the term linked with volumetric heat generation. And so we have that the divergence of K times gradient of temperature is equal to 0. So a further simplification is assumed. Now, in order to keep on with our process of simplification, we need to understand if K can be taken out the divergence. And in order to do this, we need to do hypotheses on the material. First of all, we can make an easy assumption, which is to consider our material isotropic, which means that the properties, in this specific case thermal conductivity, does not depend on the direction on which it is measured, which means that we have the same thermal conductivity along x, y and z axis. This is a relevant simplification because in the most general cases K is a matrix, and in the isotropic hypothesis K is just a number. But this hypothesis is not enough in order to take out K from the divergence, because we need to hypothesize also that K is not temperature dependent. So K should be constant with respect to the temperature, because if K is variable with the temperature and temperature is variable with the space variables y, z and x, K becomes a function of function, and therefore it is also a variable of x, y and z. So, in order to simplify the equation, we will assume that our material is isotropic and K does not vary with temperature. In this case, K can be taken out from the divergence, and the equation becomes Laplace equation. Laplacian of temperature equal to 0. So, now the equation has a much simpler form with respect to the initial one. This equation is in vectorial form. Therefore, according to the way we explicit the Laplace operator, this equation can be expressed in rectangular, cylindrical, spherical, or other system of coordinates. In our specific case, we have a planar wall, and so the most convenient choice is to express the Laplace operator in rectangular coordinates. So let's try to do it. We now express the Laplace operator in rectangular coordinates, which seems to be the best choice in our case, because we have a planar geometry. So we can express the Laplace operator as second derivative of temperature with respect to x plus second derivative of temperature with respect to y plus second derivative of temperature with respect to z. Everything is equal to 0. So this is the expression of the Laplace operator in rectangular coordinates. But this equation is valid if temperature would vary in the three directions, x, y, and z. But according to what we have previously said, in our case we have that the thickness along x is much smaller with respect to the dimensions in the y and z direction. Therefore, we can assume our problem as one-dimensional, which means that we can neglect the derivatives along the y and z direction. So we can write our equation as second derivative of temperature with respect to x equal to 0. But in this case, if temperature depends only on x, we can substitute the symbol of partial derivative with that of total derivative, because there is the dependence on only one variable. So the problem is much simpler with respect to the starting one, because now we moved from a second order partial derivative equation to a second order ordinary differential equation. So the problem is much simpler. Now this problem is not complete for our case, because in order to solve this equation, to find a specific integral, a particular integral of this equation, we need to impose the boundary conditions. In this case, we need two boundary conditions, because the equation is of the second order. We have the boundary condition on the two sides of our wall, in x equals 0 and x equal to L. Because we know that in x equals 0 there is a constant heat flux, and in x equal L a constant temperature is kept. So we need to formalize these boundary conditions. Particularly, we can write that according to the Fourier law of conduction, minus k derivative of temperature with respect to x calculated for x equal to 0 is equal to q dot. This is the first boundary condition of our equation. And if you remember from previous lectures, we have called this condition as a second kind condition. The other boundary condition is on the temperature. So we have that T temperature in L is equal to T1. And as you remember, this one was called a first kind boundary condition. So now we have our equation and the two boundary conditions. We are able to solve our problem and to find a particular integral of our equation. In order to do it, we need to integrate this equation twice, because it is an equation of the second order. So, if we integrate the equation, this equation, once, we get derivative of temperature with respect to x equal to C1, where C1 is a constant of integration. So, we can now integrate once more this equation and we get t as a function of x equal to C1 times x plus C2. As you can see, we have two constants of integration, C1 and C2. We need to determine these two constants in order to find a specific integral for our problem. So, the data for our problem are that the L is equal to 0.5 meter, Q dot is equal to 20 watt per square meters, T in L is equal to 70 Celsius degree, and the area of heat exchange is equal to 20 square meters. Moreover, K is 4 watt per meter Kelvin. So we want to solve a practical problem because we have our physical data. In order to solve our problem, we need to impose the boundary condition. We can start by imposing the first boundary condition on the heat flux. So we can write that minus k derivative with respect to x of the temperature, but now we have the profile, so we can substitute it. We have C1x plus C2 is equal to Q dot. If now we calculate this derivative, should be calculated in x equals 0, we have that minus k times C1 is equal to Q dot. Okay? So, from this equation, we can easily determine C1 as minus Q dot divided by K. This is the first constant of integration necessary to find the specific integral of our equation. Now we can apply the second boundary condition in x equal to L. And so we have T of L equal C1 times L plus C2. But C1 is equal to minus Q Q dot divided by K, and so we can substitute. So we have TL equal L minus L times Q dot divided K equal to C1 plus C2. Okay, and immediately we can determine from this equation C2 as C2 equal T in L plus Q dot times L divided by K. And now we can write the profile of temperature for our set of boundary conditions. We have that T of X is equal to C1 minus Q dot divided K times X plus Q dot times L divided K plus T in L. And now our temperature profile is determined. This temperature profile here is of general form. So it is possible to apply this equation for all the problems which have the same set of boundary conditions. The solution of the conduction equation will be always that one. Now, by substituting our values, we can determine, for example, the temperature for X equal to 0. So we have that T in 0 is equal to Q dot L divided K plus TL, which means that Q dot is 20 times 0.5 L divided by K, which is equal to 4, plus TL, which is 70. And we find that temperature is equal to 72.5 Celsius degree. This is just an example because we can determine the temperature for every X. But if we focus on this equation, we can notice that the temperature changes linearly as a function of X. So the temperature changes linearly within the plate from 70 here up to 72.5 here in X equal to 0. Now we would like to determine the heat transfer rate Q dot. In this case it is very simple because we know the heat flux and we know the heat exchange surface, so we can write Q dot times A, 20 times 20 equal 400 watt. In this way we have determined Q dot. Another way could have been to apply the Fourier law, but of course it is more complicated, but anyway is also acceptable because you could have written Q dot equal minus K times A times derivative of temperature with respect to X. You know the temperature profile, and so you can make this derivative and determine the heat transfer rate by conduction. As you can see, it is more complicated with respect to this other approach. So, in this lecture, we learned how to solve the heat conduction equation when a boundary condition of the first kind, so a constant temperature, is applied, and a boundary condition of the second time, which implies the knowledge of the derivative of temperature on the boundary, is applied. Thank you very much for your attention.